Hi everyone, and welcome to the video for section 5.7 of our book on the inverse trig functions with integration. So with this one, our objectives for this particular video are: one, to integrate functions whose antiderivatives involve inverse trig functions; number two, use completing the square to integrate a function; and number three, review the basic integration rules. Now, the first thing I'd like you to do is recall the stuff that we did last time. And the three that I'd like you to recall are that the derivative of the inverse sine is 1 over the square root of 1 minus x squared. That the derivative of the arctangent is 1 over the x squared plus 1 or 1 plus x squared, depending how you look at it. And the derivative of arcsecant comes out to be 1 over the absolute value of x times the square root of x squared minus 1. Now we want to use those three because those are the, we know that the other three are just the opposites of these negatives of those. And so when we look at these, we know that what the derivatives of these functions are. So therefore, I can say what happens, because of the relationship between derivatives and integration, I can say what the integral of each of these would be. And so what we have is, in terms of, now keep in mind that these were very specific in terms of 1 and the x. Those could be different. So what we're going to do is look at this in terms of where we have something other than 1 there and something other than x. So we have the integral, the first one, the integral of du over the square root of a squared minus u squared, where a is a real number and u is some function of x, is going to be the arcsine of u over a plus c. Then the integral of du over the a squared plus u squared, in this case it looks a lot like that arctan, is going to be 1 over a times the arctan of u over a plus c. And then the integral of u times the square root of u squared minus a squared is 1 over a times the arcsecant of the absolute value of u over a plus c. These three formulas here are going to be ones that you're going to want to spend time and make sure you have memorized, along with the other formulas that we've used so far, and that we'll take a look at again at the end of this, at the end of the chapter of the section in the book. Now let's take a look at a couple examples. In the first example, what we have is that we're looking at the integral of dt over the square root of 9 minus 4t squared. Now in that case right here, we look at this, and right away, because it is underneath the square root, it's a constant minus the function of t, in this case of something with a variable, I am thinking of the arcsine function. As I look at that square root is in that arcsine form. And so I look at that, I realize that 9 is 3 squared, and 4t squared is the quantity 2t raised to the second power. And so what I'm going to do on this one is I can think of that that the 2t is u, so I'll let u equal the 2t, and therefore du is going to be 2 dt. Well, notice I don't have the 2, so I can put the 2 here. I can put the 2 there, but remember, if I put a 2 there, I have to have a 1/2 on the outside. And now what I have, this is all in the form of the arcsine function. And so I know that u is 2t. Thinking of the formula, u is 2t, a is 3, and this up here is du. And recalling that the integral of du over the square root of a squared minus u squared is equal to the arcsine of u over a plus c. This particular function that I'm working with here, this one, that is now in that form where u is 2t, a is 3, and again, this up here is du. So I know that is going to end up equaling 1/2 times the arcsine of 2t over 3 plus c. And that would come out to be the integral of dt over the square root of 9 minus 4t squared. Looking at number 2, right now, a lot of times when people look at this, they look at this one and they say that they feel like this is going to be the inverse secant. And a lot of times the reason when I ask people why they say they think this is going to be the inverse secant is because of this x out here. Again, don't go by that. Don't go by the fact that something is out there. Go by looking at what's underneath the square root. In this case, I look at that. That's a square root of a 9x squared minus 25. And so I recognize that as being that inverse secant. And of course, I can recall that the inverse secant says that the integral of du over u times the square root of u squared minus a squared is going to be 1 over a times the arc secant of the absolute value of u over a plus c. So in this case, what's really going to be key on this is that I recognize u and that I have the du as well. So I can work with that as well in the problem. So the first thing I'm going to do with this one is I'm going to take that 2 and I'm going to bring it out. So that's going to be 2 times the integral of dx over x times the square root of the 3x, that quantity squared, minus 5 squared. Now looking at that, I again recognize the fact that in this case, I can let u equal to 3x. So in order for u to be 3x, I know that, and right now I look at what I have on the outside. I don't have u, so I need to put a 3 there. And of course, I can't just put a 3 there. I'll have to put the 3 up there as well. So these two 3's I've now added will then cancel each other out, okay? But it puts it into the form that I need. And you'll notice in this case that if u equals 3x is equal to 3x, du is going to be 3 dx. So right now, there's the du. That's u, and u squared minus a squared. And so by applying this formula here, I know that this integral here is going to equal 2 times 1 over a, so 1 over 5, times the arc secant of the absolute value of 3x over 5 plus that c at the end. And so, in this case, I end up with, I shouldn't have put that line down there, but that's okay. I end up with 2/5 arc secant of the absolute value of 3x over 5 plus c as the integral of that function. Now let's take a look at a third example. The integral, what we're looking at for number 3 is we're looking at the integral of sine x over 7 plus cosine squared x. Now, in this case, in this case, you might be first looking at this thinking maybe just a direct u substitution, because I look at that, I notice that in the denominator I have a cosine. Derivative cosine is a negative sign. But I do have the sign in there. It's just a sign change. And so you look at that and think, well, maybe I can use that. Well, the problem you have is that squared right there. The derivative of that denominator is going to be 2 times cosine x times the negative sine x. So in this case, the u substitution won't work. So what I'm going to look at then on this one is let's think about the inverse trig functions. So this particular function now is going to be equal to the integral of sine x over the square root of 7 squared plus the cosine of x squared. And this is dx, and I should have a dx there too. So now, once I do that, I look at this, and again, we mentioned that we can think of u as now we can look at this in terms of, if we think of this as an inverse tangent, we can think of the u as cosine x, so therefore du is going to be a negative sine x. So I just need to, at that point, put the negative sign there, and of course there's going to be a negative sign on the outside as well to go and compensate for this. So now at this point we do have the inverse tangent, and so I can apply that formula for the inverse tangent, and I know that this is then going to equal the opposite of 1 over a, which is the square root of 7, times the arctan of cosine of x over the square root of 7 plus c. Now for problem number 4. Problem number 4 I put in there just because it is very different, and it is a type of problem that you could see. And what we're looking at here is the integral of the arcsine over the square root of 1 minus x squared dx. Well, in this case, when you look at this one, what you really want to recognize here is that this function can actually be written as the integral of the arcsine of x times 1 over the square root of 1 minus x squared dx. And so with that, what I can do is I can go and let u equal the arcsine of x. Du then is going to be 1 over the square root of 1 minus x squared dx. And so you see this integral now has become, just with a simple u substitution, it is now the integral of u du, which comes out to equal 1/2 of u squared plus c, or equal to 1/2 times the arcsine of x, that thing squared, plus c. So keep in mind as you work on these things that just because of the function where we're at does not necessarily mean that you're going to have to apply the integration formulas. You're just going to have to recognize that we could end up involving one of those formulas. But as in this case here for this particular problem, really it would ended up being just a power rule problem. Now the next thing we have to deal with as well is the integration with completing the square. So what this does, we're going to go through, take a problem that we can't integrate with the formulas that we have right now, and we're going to modify it. We're going to change it up so that it looks like something that we can actually apply some of these inverse trig integrals to. For example, let's look at this problem here. We have the integral of dx over x squared plus 4x plus 13. Now in this case, you might start out, first things people think of is, I'll let the denominator equal u and see if that works. In this case it won't, because the derivative of that denominator is going to be 2x plus 4. I could deal with the constant, the 4, but I can't deal with the fact that we have to have a 2x, because there's no x up here. I can't just add a variable into this problem. So I want to look at a different way, and what we're going to do is we're going to go and complete the square. So remember from last year what we talked about with completing the square. What I usually do is I'll isolate everything with an x by putting the parentheses on there. And so that is then going to equal the integral of dx over the x squared plus 4x plus blank there, and then a minus blank on the outside, and plus the 13. Now remember here on this problem, I kind of skipped a step because what we did last year is I asked you to go through and determine if you could complete the square on this thing. The fact that the coefficient on x squared is 1 tells me that I can. So remember on this, what we have to do now is fill in the blank, and what I have on this problem is that I'll take half of the 4, which is 2, and so what I'm going to put in there in the blank is going to be a 2 squared. And remember again, and go through and whatever you put in there, you have to subtract. So 2 squared is 4, so I'm subtracting 4 on the outside there. So now, when I simplify this problem, that is going to become the integral of dx over The reason we complete the square is how that's going to factor. That is going to factor as x plus 2, that quantity squared, and then it's going to be minus 4 plus 13 is going to be plus 9. So now I can look at that problem, and you should be able to recognize that we do have the inverse tangent here. That we're dealing with two things squared. That 9 is 3 squared. These two things squared and the addition there. So I'm looking at inverse tangent. Also notice that u is x plus 2, so du is just going to be dx. So we're all set with that as well. And so this problem here, as I mentioned, is the integral of dx over x plus 2, that quantity squared, plus 3 squared. So I know the u is x plus 2 and a is 3. And so that's going to be equal to the arctan, 1 over 3 times the arctan of x plus 2 over 3 plus c. So notice how the completing the square helped us get it into the form that we could then go and integrate. At this point, we have reached the end here of this video, except for I would like you to go and turn to page 378 of your book and make sure you review all 20. There are now 20 basic integration rules that you should be familiar with, to the point that you can apply them whenever you happen to need to, and that you are very, very, very familiar and very comfortable with them. So make sure you look over those, and with that, we will go and call this video complete. And I hope that you have a good evening, and we'll see you in the next class.